Good good morning, yeah, or good afternoon, yeah. Okay, so I'll be talking on investigating higher fringing flux of an air gap system with relative losses. My name is Dr. Christopher Oluwatobi Adeogun from South China University of Technology, China. So I'll be starting from my abstract. And we know that the amorphous or nanocrystalline gap cores, as well as powdered cores, are both popular in industrial choke design. Right? So, but they show different advantages and drawbacks depending on their function within a circuit. So in this paper, we present the design approach, combining both core materials, right, for choke design. The drawbacks of air gap solutions are shown. And compared to other solutions, so where the air gap is replaced by a distributed gap using a piece of powder material as well. So we illustrate the much higher fringing flux of an air gap structure and related losses, the design procedure of an inductor using a powdered material instead of an air gap, and the different saturation behavior of both solutions are shown. So for power inductors, which are mainly storage chokes working at nominal current in a range of 50 to 200 amperes, and the frequency between 3 to 100 kilohertz, often gapped amorphous or nanocrystalline cores are used. So they offer a much higher possible saturation flux density, known as BSAT, compared to ferrites, right? So what also makes them the preferred choice to build smaller inductors is because they offer a much higher possible saturation flux density. And also to store a high amount of energy, power inductors built from amorphous or nanocrystalline materials require a relative large air gap in the range of 2.10 millimeters. Fringing flux entering the space around a big air gap is problematic due to forced eddy current losses. The ways to overcome this problem are the usage of multiple small air gaps, what causes a larger manufacturing effort, or the usage of lower permeability powder materials with a permeability μr of 10 to 26 inserted instead of an air gap. So we are going to make use of lower permeability powdered materials instead of an air gap, which is the approach shown. While combining two materials to form a core without an air gap, both should have a usable flux density, BUs, in the same range. So the send-dot material is the QMU material, has a soft saturation curve with a BSAT in the range of around 1 terabyte. And the preferred range of BUs in amorphous and nanocrystalline cores is due to core loss effects, also in the range up to 1 T. Fringing flux and eddy currents appears at any kind of discontinuity within the core, like air gaps or edges. And the following figure illustrates the fringing flux entering the winding at an air gap inductor with an E-core, where the flux lines are entering the windings with high intense strong electric fields, right, minus E, are induced following Faraday's law, equation 1, which leads to high eddy current density. So because of the induced Faraday's law, which leads to the high eddy current density, right, the high conductive material of the windings would have minus JE. So we can see from the illustration below, following the Ohm's law, and we're going to see the equation 2 shortly. So now we have the equation as shown, and the eddy current, and so the losses around the air gap due to fringing flux are proportional to the level of the magnetic flux density B and its frequency. That's the equation for equation 1, but we have the equation 2 above. So these losses can lead to hot spots inside the winding and the choke, having a negative impact on the electrical behavior and lifetime. So to avoid them, by a rule of thumb, a space between the windings and the core at the air gap should be twice the gap size. For larger air gaps, this value has to be increased significantly as the fringing flux effect increases as well. What reduces the space for the winding one? So because of the larger air gaps value will be increased significantly due to the fringing flux effect, this will reduce the space for the winding. So if laminated cores, like we have the nanocrystalline ion or the amorphous are used, higher heading currents are also induced there. So as the direction of the fringing flux is orthogonal and not parallel to the isolated laminations when it is leaving or entering the core. We can see that in figure 2 shortly. So we have this. So we can see from the figure, the Y and the X axis. And from the illustration, if the laminated cores are used, higher eddy currents are also induced there. So as the direction of the fringing flux is orthogonal and not parallel to the isolated laminations when it is leaving or entering the core, as shown in this figure. We compare the flux density around an air gap to the flux density around a cool MU block with a permeability of mu initial, which is equal to 26, which is used as magnetic resistor instead of the air gap. So we employ the cool MU block with the permeability of mu initial, which is equal to 26, is used in replacement of the magnetic resistor, which is used as a magnetic resistor, pardon me, instead of the air gap. So this is employed in replacement of the air gap. So both designs end up having the same AL value at the operation point, same excitation applied, as we can see from the figure, and so form the same inductance in the core. The flux density inside the cool MU block is around 400 meters, right? Calculated with a finite, it is calculated with a finite computation of elements. And at this level of flux, both gap structures have the same magnetic resistance. They are excited with the same magnetomotive force, theta. And how to calculate the length of a piece of powder material to replace an air gap concerning its soft saturation curve will be discussed. So we have two axes, X1 and Y1 as shown. They refer to the axis in the diagrams in figure 4 and 5. So we are going to be seeing the figure 5 shortly, which show the total flux density along these traces. So we can see for the cool MU block, which is used in replacement of the air gap. So the red line is speaking about the air gap, while the blue is the cool MU block in replacement of the air gap. So the other figure, figure 5, the part X1 has a distance in the range of the size of the air gap size from the core. So figure 4 illustrates the peak flux density in this distance of the air gap structure to be approximately 5 times higher than using the cool MU block. So let's look at the calculation of powder material block size using the analytical method. We show the calculation of the length of a powder core block to replace the air gap within an amorphous or nanocrystalline material, as both amorphous and nanocrystalline ion cores have a much higher permeability of mu Fe greater than 8.00, and the designer can assume that the O magnetomotive force theta is applied on the powder material as it would be on the air gap. This is the case as long as the flux density in the ion material is not in the range of the saturation flux density, BSAT, as then also inside the ion, the permeability drops significantly. So we show the relation of their effective permeability, mu efficiency, to their initial permeability, mu initial, and is given by the powder core manufacturer. So we have the mu efficiency over the mu initial is equal to F into H, and that's the third equation. And the H field in the powdered block equals to H equal to theta over L powder equal to capital N, right, dot I over L powder. So we are assuming that the mu Fe is much greater than the mu powder in this equation. Okay. So in the algorithm one, the iterative calculation of powder block length. So when using the above shown analytical way to calculate the length of the powder block, the following issues have to be considered. So we have to know that unlike an air gap, the permeability of the powdered material is not only influenced by saturation, but also by temperature, mechanical stress, and operation frequency. And this eventually has to be considered in the above shown algorithm that we just saw. And in reality, the effective permeability, mu efficiency, and so the resulting L final are smaller than the analytical calculated values. This is due to less fringing flux and a higher percentage of flux inside the powdered core compared to the air gap solution, which results in a higher saturation in the powdered material. To detect the fitting length, a finite element method is used to analyze for proper analysis, or the construction of a prototype using several small powder material slides can be used. So we can either use a finite element method to analyze, or we can construct a prototype using several small powder material slides. So we also know that the equation 3 is a fitting function which does not work in high saturation cases. So let's look at the air-gapped nanocrystalline. We show at a concrete example how an air gap is replaced by a piece of powder material, and in this case, a cool mu block. It is demonstrated how the fringing flux that is entering the space around the air gap, and so the winding is reduced. The storage choke works on a direct current of 48 amperes with a 20 kilohertz ripple of delta LPP, which is equal to 12 amperes. So a change in the powdered material, right, with a 20 kilohertz ripple, right, and a DC current of 48 amperes is actually illustrated, and it is shown in the following curve. Its inductance is 290 mu H until it starts saturating. Following the calculation, the saturation will be reached at around L sat, that is at the saturation point, which is equal to 100 amperes, which corresponds to a flux density of 1.2 Tesla. So we can see from the figure, voltage leads current by 90 degrees in phase, and we have the voltage and the current, right? So at 90 degrees. So voltage will lead current by 90 degrees in phase. As we can see, the dark curve is the voltage and the dotted red curve is for the current. The choke is constructed with a nanocrystalline core. Its cross-section is shown in figure 7 below, and the height of the core is 35 millimeters, and the magnetic path in this design contains 2 equal air gaps. Each has a length of 3.5 millimeters. The 44 turns are wound by 6 parallel strands of copper wire with 1.5 millimeter diameter, as shown in figure 7. In this design, the distance of the winding from the core is 3.5 millimeters. During normal operation, the nominal flux density, Bn is denoted as the nominal flux density in the nanocrystalline ion, is at 0.54 Tesla, and the AC current forces a change in flux, delta B, of 0.132 Tesla. So we can see this is the nanocrystalline ion, right? And we can see the winding. And also the cool Mu material, sandust 26, right? So we can see that from the design, the distance of the winding from the core is 3.5, is assumed to be 3.5 millimeters. And during normal operation, the nominal flux density B in the nanocrystalline ion is at 0.54 Tesla. So let's look at the replacement with cool Mu26, which is the material that replaces the air gap. So both air gaps are replaced by a block of cool Mu powder material with an initial permeability of mu initial, which is equal to 26 sandust, as we can see from the previous diagram. The drop of the initial permeability of this material due to an applied DC direct current is shown in the following figure, right? And using the algorithm 1 and equation 3, we receive the total powder length of 127 millimeters. So both the material, the sand dust material, replacing the air gaps, have a length of 63.5 millimeters. The nanocrystalline ion cut core has to become smaller, which is no problem due to its fabrication procedure. So the complete design with its flux density plot is shown in figure 6. It shows the overall design to have the same size as the solution with the air gaps shown in figure 7. So this is the figure 8. We can also see the nanocrystalline ion, the winding, and the air gap, both air gaps, right? So we know that the replacement is done using the sand dust material. And also, the nanocrystalline ion cut core has to be smaller. And also, when designing, we can see that if you also want to design or construct without actually using the framework that is existing, the complete design is shown in figure 6, which we've seen previously. And it is also known that the overall design is to have the same size as the solution with the air gaps. So the sizes should not vary. So even when you are constructing your own, system, you should take note that the sizes of the air gaps should be the same. So it shouldn't vary. Comparison of both designs. The flux density of both designs when excited with the nominal current 48 amperes is shown in figure 9. Using the same grayscale in both figures, it is clearly shown that the air gap makes the flux like the DC flux, also the AC flux, forced by the alternating current, which is shown in figure 6. And this must be very, I'm going to use the word, this must happen using the same fringing at the air gaps. So there shouldn't be differences. This shouldn't vary. So it should be the same. The size of both air gaps should be the same. So the path of the alternating flux penetrating the winding will force high frequent eddy currents in high conductive paths like the winding. This will lead to losses and hotspots at the winding next to the air gap. So with the design where the air gap is replaced by a block of cool Mu powder material, these losses and the local temperature rises are eliminated. So definitely there will be losses due to air gaps. So the AC flux density along parallel traces in a distance of 2, 4, 6, and 8 millimeters from the left leg of the 1272 cores shown in the figure 7 and 8 was numerically calculated using the FEMM, that is the finite element methods. So now we can see the core type construction and the shell type construction, and we can also see that the flux in the same distance from the core, but inside the winding window, right direction from the left leg is shown. So the flux is the same from the core, right? So we can also see the primary and second windings. We see the magnetic lines of flux, right? And then we see the core. And this is at high voltage and low voltage. And we can actually spot the differences, right? As stated, both designs result in chokes with the same size and shape. Both have the same number of turns and windings and winding size. Due to the different construction of the core, the two chokes show a different direct current behavior. So the solution with the powder block starts at a high no-load inductivity and shows the typical soft saturation curve of powdered material, while the design with the air gap core has a constant inductivity up to its saturation point at around 100 amperes. The inductivity in the operation area is for both chokes at 290 μH. So as we can see, this is sand dust material, and at a high no-load inductivity, This shows the typical soft saturation curve of powdered material. So while the design with the air gap core has a constant inductivity up to its saturation point, the inductivity in the operation area is for both chokes. So we can see the temperature and also the permeability, right? So this is for the sand dust material. And in conclusion, in this paper, we presented the approach to combine the ion-based cut cores with powdered materials to avoid fringing flux and its negative effects. Using the presented design approach enables the designer also to build smaller inductors, as a large distance is not required. So if the hair gap is replaced with powdered material, we know that the powdered material sand dust is replaced with an air gap instead of using a powdered material. So we have presented this approach to combine both cut cores with powder materials to avoid fringing flux and its negative effects, because we know that losses are evident and we want to reduce those losses as much as possible. Thank you very much. And the references are taken from the following: High Frequency Magnetic Components by Willy, second edition, 2014, and Transformers and Inductor Design Handbook, Inductor Cores, Material and Shape Choices. That's the technical report of magnetics. And also Powder Core Catalog, 2015, Power Conversion and Line Filter Applications of Micrometals. Thank you.